All right, let's go. Number 7. The bloop. In 1997, NOAA hydrophone arrays picked up something, a sound, deep in the Pacific Ocean. And not just any sound, the loudest unidentified sound ever recorded in Earth's oceans. They called it the bloop. Here's what made it strange. The acoustic profile matched something biological. The shape of the signal, the way it rose and fell, looked like it came from an animal. But the scale didn't fit any animal we know. To produce a sound that loud, at that frequency, from that depth, the creature would have to be enormous, larger than anything currently cataloged in marine biology. Scientists tried to explain it away. Ice quakes, tectonic movement, underwater fracturing, and those are legitimate candidates. But none of them fully match the original recording. Not the exact shape, not the exact rise. The signal is detected by sensors nearly 5,000 kilometers apart. Think about that. 5,000 kilometers. That's the width of a continent. Whatever made that sound was powerful enough to travel across an ocean. We still don't know what it was. NOAA has revisited it, researchers have analyzed it, and the best current explanation, icequake activity, remains contested. What we do know, something generated that signal, something real, something physical. And whatever it was, it has never been heard again. That's number 7. And compared to what's coming, the bloop is almost comforting, because at least it happened on this planet. Number 6. The WOW signal. August 15th, 1977, Big Ear Radio Telescope, Ohio State University. A volunteer named Jerry Amon is reviewing data printouts, and he sees something, a sequence of alphanumeric characters stretching across the page. So striking, so anomalous, he circles it in red pen and writes one word in the margin. Wow! That's how it got its name. Not from a committee, not from a press release, from one scientist, alone at a desk, staring at something he couldn't explain. The signal lasted 72 seconds. It came from the direction of the constellation Sagittarius. It matched almost exactly what scientists theorized an extraterrestrial transmission would look like. Frequency, bandwidth, intensity, all of it. Here's the part that doesn't sit right. It was never detected again. Not once. Dozens of follow-up observations, multiple telescopes, decades of listening. Silence. A signal that arrives once, perfectly, and then disappears forever, that's not how natural phenomena behave. Natural sources repeat, they fluctuate, they persist. This one didn't. Some researchers proposed it was a comet, hydrogen gas clouds, reflected signals, but those explanations came years later, and they remain disputed. The WOW signal sits in the literature as the strongest candidate for non-terrestrial radio contact ever recorded. Not confirmed, not explained, just there. A single data point, 72 seconds long, filed under unknown. That's number 6. But a signal you can't explain is one thing. A star that breaks the laws of physics is something else entirely.
Number 5. Boyajian's star. Most stars are predictable. They dim slightly when a planet passes in front of them. A small dip, regular, repeating. That's how we find exoplanets. We know exactly what that looks like. Boyajian's star doesn't do that. Also called KIC 8462852, this star was flagged by citizen scientists combing through Kepler Space Telescope data in 2015. And what they found had no category. The star dims dramatically, up to 22% in brightness, far beyond anything a planet could cause. A planet the size of Jupiter only dims a star by about 1%. 22% means something enormous, something that doesn't fit. But it's not just the depth of the dipping, it's the shape. Irregular, asymmetric, unpredictable. Sometimes it dims for days, sometimes hours, sometimes the pattern clusters, sometimes it doesn't repeat for months. No known natural structure produces this. Not dust clouds, not debris fields, not any configuration of orbiting bodies that obeys the physics we understand. And then there's the long-term dimming. Over more than a century of photographic records, Boyajian's star has been slowly fading, gradually, consistently, as if something is being built around it or closing around it. Researchers have proposed cometary swarms, interstellar dust, internal stellar behavior. None of it fully holds. The star keeps dimming, the patterns keep shifting, and the models keep failing. That's number 5, a star we can see, study, and measure, and still cannot explain. But what if the signal wasn't even light? What if it arrived in milliseconds from billions of light years away and carried more energy than you can imagine? Number 4, fast radio bursts. Imagine a flash, not of light, of radio waves, lasting less than the blink of an eye. That's a fast radio burst, a pulse of radio energy so brief, so violent, that by the time your instruments register it, it's already gone. The first one was discovered in 2007, hidden inside archival data from 2001. A signal so strange, researchers assumed it was interference, instrument error, contamination. It wasn't. These bursts originate billions of light years away. In milliseconds, less time than it takes to blink, they release more energy than the sun emits in 3 days. Some estimates say weeks. Think about that scale. Our sun, 3 days of total output, compressed into a millisecond from across the observable universe. We don't know what produces that. Nothing in our models generates that ratio of energy to time. Not neutron stars, not magnetars, not any process we've confirmed. And then it got stranger. Some bursts repeat. Same location, same signature, firing again and again at irregular intervals. That rules out cataclysmic one-time events. You can't have an explosion that happens twice. FRB 20121102A, the first confirmed repeater, has fired hundreds of times from a dwarf galaxy 3 billion light-years away, still firing, still unexplained. Proposed sources include magnetars, cosmic strings, and structures we haven't named yet. None fully account for the repeating ones. None close the gap between theory and observation. Fast radio bursts are now detected almost daily. We're getting better at finding them. We're not getting better at explaining them. That's number 4, a phenomenon we can detect, catalog, and count, but cannot classify. But at least fast radio bursts travel across space. What if the anomaly wasn't a wave, wasn't a signal, but a single particle? One particle moving at a speed that should be impossible.
Number 3, the Oh My God particle. October 15, 1991, a cosmic ray detector in Utah picks up something it was never designed to handle. A single subatomic particle. One particle. Hitting the atmosphere at a speed so close to the speed of light that the difference is almost unmeasurable. Scientists calculated its energy, then calculated it again. 3 × 10 to the 20th electron volts. That number needs context. The most powerful particle accelerator humans have ever built, the Large Hadron Collider, accelerates particles to about 13 × 10 to the 12th electron volts. The Oh My God particle carried roughly 40 million times more energy than that. One particle, no machine, no accelerator, just arriving. Here's where physics breaks. There's a theoretical limit to how much energy a cosmic ray particle can carry across intergalactic distances. It's called the GZK limit, the Grayson-Zatsepin-Kuzmin limit. At a certain energy threshold, particles traveling through space collide with photons from the cosmic microwave background. They lose energy. They have to. The universe itself bleeds them dry. The Oh My God particle exceeded that limit. Not by a small margin, not within measurement error. It blew past the theoretical maximum like the limit wasn't there. Which means one of two things. Either the particle originated so close to Earth that it didn't have time to lose energy, meaning something nearby produced it, something we've never identified. or the GZK limit is wrong, and the physics we use to describe how particles interact with the universe is incomplete. Both answers are deeply uncomfortable. Similar particles have been detected since. The telescope array in Utah continues to find ultra-high energy cosmic rays that push against the boundary of what theory permits. We still don't know where they come from. We still don't know what accelerates them. No known astrophysical process produces energies at this scale. Not supernovae, not gamma-ray bursts, not active galactic nuclei, at least not by any mechanism we can confirm. That's number 3, a particle that broke the rules simply by existing. But particles can be small, localized. Maybe we missed something in the model. What if the anomaly wasn't a particle, but an object, a radio source, pulsing on a schedule that no known physics can produce?
Number 2, Gleam X J162759.552350.3. In 2022, astronomers in Australia were reviewing data from the Murchison Wide Field Array, a radio telescope scanning the southern sky. And they found something pulsing. Not unusual on its own. Pulsars pulse. That's what they do. Rapidly rotating neutron stars emitting beams of radio energy like cosmic lighthouses. We know how pulsars work. We've cataloged thousands of them. This wasn't a pulsar. Gleam X J162759.552350.4.3 pulses every 18.18 minutes. Let that settle. 18 minutes. Known pulsars rotate in milliseconds, seconds at the slowest. A neutron star spinning slowly enough to pulse every 18 minutes should not be producing radio emission at all. By the time a neutron star slows to that rotation rate, its magnetic field has decayed. Its emission mechanism has shut down. It goes quiet. Physics says this object should be silent. It isn't. For about 3 months, it pulsed with extraordinary brightness, one of the most radiant radio sources in the sky during each burst. Then it stopped and went silent. The research team searched archives looking for historical detections. Nothing. No prior signal, no earlier pulse. It appeared, it broadcast, it vanished. Proposed explanations include ultra-long period magnetars, a class of object that is almost entirely theoretical. We've never confirmed one. Others have suggested white dwarf pulsars, a rare, barely understood category with only one confirmed example. Neither explanation fully fits the energy output, the period, the disappearance. What makes this entry sit at number 2 isn't just that we can't explain the object. It's that the object shouldn't be able to do what it demonstrably did. It violated the expected life cycle of stellar remnants. It pulsed when it had no mechanism to pulse. It disappeared when it had no reason to stop. An object that breaks its own category simply by functioning. That's number 2. But a single anomalous object, strange as it is, exists somewhere out there, distant, contained, bounded. What if the anomaly wasn't a star, wasn't a particle, wasn't a signal from across the galaxy? What if it was embedded in the oldest light in the universe, a flaw in the very fabric of what the cosmos should look like, staring back at us from the beginning of time itself? 13.8 billion years ago, the universe was a single, hot, dense, screaming plasma. No stars, no galaxies, no structure, just energy. Everywhere. Uniform. Identical. About 380,000 years after the Big Bang, that plasma cooled enough to release light for the first time. That light still exists. It fills the entire sky, every direction, every point. A perfect afterglow of the birth of everything. We call it the cosmic microwave background, the CMB. It is the oldest thing we can observe, a snapshot of the universe before anything existed. And it should be almost perfectly uniform. Tiny fluctuations, microscopic variations, the seeds of future galaxies, all within expected ranges, all within the model. Except for one region. In the direction of the constellation Eridanus, there is a patch of sky, roughly 5 times the diameter of the full moon, where the CMB is measurably colder than everything around it. Not slightly colder,
statistically dramatically colder, so anomalous that the probability of it occurring by chance within our standard cosmological model is less than 0.3%. We call it the cold spot. The simplest explanation, a statistical fluke, barely holds. The more serious explanations are harder to sit with. One proposal, a supervoid, a region of space nearly empty of matter, so vast, roughly 300 million light-years across, that photons passing through it lose energy, arriving colder than everything else. A supervoid has been identified in that direction, but it doesn't fully account for the temperature difference. The math doesn't close. And then there's the other explanation, the one researchers mention carefully, a collision. If our universe is not the only universe, if we exist inside a multiverse of parallel bubble universes expanding alongside our own, then in the earliest moments after the Big Bang, our universe may have collided with another one, a bruise left in the fabric of space, visible in the oldest light we can detect. That bruise is the cold spot. No other explanation fully fits. Not the supervoid, not statistical noise, not any single mechanism our current models can generate. And here is why this is number one. Every other signal on this list is something we received. A sound, a pulse, a particle, a transmission, something that arrived and we couldn't explain the source. The cold spot is different. It isn't a signal from somewhere out there. It's a scar on the beginning of everything, a mark left in the structure of reality itself from the moment the universe began. If it's real, if it's a collision imprint, then we are not alone in the most fundamental sense possible. Not alone in the galaxy, not alone in the cosmos, not alone in existence. And we've known about it for decades, photographed it, measured it, mapped it in extraordinary detail. We just don't know what it means. 7 signals, 7 things we detected, measured, recorded, and could not name. Maybe they all have answers, simple ones, waiting in data we haven't collected yet. Or maybe some of them are pointing at something our current understanding genuinely cannot hold. Either way, we're listening. And something, somewhere, might be too.